Okay, good morning. I hope that you have enjoyed your holidays, and then let us go back to business now. So today I want to talk about another form of a complex number, which is called the exponential form of the complex number, and that's actually a very important topic as well. So there is a formula involved here in this topic called the Euler's formula, but we cannot prove it at this level, but I just want to motivate you why it might be right, okay? So the point is that we want to talk, so you know that the Euler number E, you know it from Math 3C, it's approximately 2.72 if you want to keep 2 decimal points. And then we know that this number is an irrational number. So this is a very famous number, actually, in mathematics. Okay, so today we want to talk about what happens if I have a complex number we want to have an idea what does it mean when we say e to power z. Yes, because so far we haven't talked about exponentiating complex numbers. We have multiplied them. Of course, so this is different, you know. If I give you a complex number, I can raise it to some power 2, 3 and ask you to calculate. Even if I ask you what is z to power minus 3, it becomes 1 over z to power 3. But this time, the power, the exponent is a variable number, z, and the base is a constant. So we haven't talked about these things so far, yes? Okay, so I'm just motivating you. That's not a proof, but I try to motivate you why the formula, Euler's formula, might be right, yes? And then, of course, after that, we will use it freely. Okay, so this is, we want to get a meaning for this, where z is a complex number and e is the Euler number. But before tackling the most general problem here, let me just consider some special case in which z is a pure imaginary number. Yes. So for the time being, let us assume that z is equal to I theta, and theta is a real number. And then we want to see what can I say about f of z in this case, which is e to power I theta. Yes. So we want to understand a little bit about e to power I theta. That is a complex number, but a pure imaginary complex number, meaning that its real part is 0. Okay, so to do that, I define a function, f of theta, to be this function, e to power I theta. I myself define f theta to be this, and I also define another function which might seem a little bit strange why I want to do it, but you have to be patient to see why it works. So I define it as cosine theta plus I sine theta. So far what I have done, I have defined 2 functions for you, one function in this form, another function like that. Another assumption that I want to consider is that whatever you learned about derivatives for real functions also applies for the derivative of complex functions, but that is not a trivial leap to take. You know, you have to talk about what do we mean by the derivative of a complex function, and then what are the rules for differentiating the complex functions and things like that. Okay, so we put everything under the rock, and then we assume that, which is a correct assumption if you go to higher mathematics, you will see that whatever you learned for differentiation, the real functions will also apply for the differentiation of complex numbers. Sorry, for complex functions. Okay, so this is why I want to take the derivative of this function with respect to its variable theta. Yes? So I take the derivative of this function, and let us see what happens. Assuming that everything is as before, the derivative of cosine theta becomes minus sine theta, and then I is a constant, so I just take the derivative of sine, which becomes cosine theta. Yes? And then what I do, I take an I out. This becomes minus 1 over I sine theta. And this one, I pulled the I out, so cosine theta is left. But you remember that what is 1 over I? So 1 over I can write it as 1 over I can rescale it by I over I. And then the numerator becomes I, the denominator becomes I squared. And this becomes I over minus 1, which is minus I. So 1 over I is minus I, so this means that minus 1 over I is positive I, yes? So this calculation shows that 1 over I is negative I, so this means minus 1 over I is positive. And then what I can do, I can go back and replace this with positive I again, and I rearrange it, meaning that I write this one first, and I write this one, and then I sine theta. Yes? So I introduce a function. What I did, I differentiate that function, and it becomes I, the same function itself. Yes, you see that this part is nothing except g of theta. So what I did, I differentiate the function that I introduced, and then it becomes I times the function itself. So if I want to write something, what I learned is that g of theta prime is equal to I times g theta for all theta in R. Okay, but then this means that g prime of theta divided by g theta is I. But I hope that you remember this combination should look familiar to your eyes. You have the derivative of the function in the numerator, the function itself in the denominator. So that is the derivative of which function? Do you remember? So I can write this as the derivative of some function equals to I. What that function is, do you remember?
ln of x.
ln of x, which is in this case ln of what? G of theta, yes? So it becomes, if you want to take the derivative of ln, you remember ln of u prime is u prime divided by u. This we had when we studied the chain rule and when we studied the derivatives of logarithmic functions. So for the right hand side, for the left hand side, I can write this. And then this is something whose derivative is this constant number I. So this means what? It means that L of g of theta is a number, is a function whose derivative is I. So hopefully it is clear this should be I theta, but probably plus a constant which we don't know yet. Yes? I have a function whose derivative is I. You remember, if I ask you a function whose derivative is 2, 3, you would say 2x, 3x or something, but the variable here is theta and the constant here is I, so you will answer I theta, but plus some constant that I don't know. I am looking for g theta. ln of g theta is equal to that. So this means that g theta, ln of g theta is I theta plus c. It means that what is g of theta? G of theta is e to the power of theta plus c. Yes? And then what can I write? I can write it as e to power c, e to power I theta. I'm telling you that this is not a mathematical proof at all, because we don't know what is the meaning of derivative of complex functions. But assuming that they are also the same, which is a true assumption, in the future if you go to mathematics you will see that, and then you will get this. So what is important is that of course still I don't know this c. Yes? By the way, now look, f of theta is e to power I theta. So this means that I found a connection between this function and this function, yes? So I realize that g of theta g of theta is e to power c, which is still I don't know c, but I have e to the power of I theta, which I introduced to be the function f of theta. And I would write for all theta in R. So at least we found a connection between this function that I am interested to know something about and this function that I artificially introduced you here. But at least now you see the connection. Yes? But this formula is valid for all theta. Yes? The only problem with me is for me is just this c, which I don't know. And then because this is valid for all theta, this means that this is also valid for 0. Yes? So if that is valid for all theta, I expect that this should also be valid for theta equals to 0. But this is easy to calculate, but because what is g of 0? Instead of theta, I put 0, it becomes cosine 0 plus I sine 0. But cosine 0 is 1, sine 0 is 0, so g of 0 is nothing except 1 is equal to e to the power of c times f of 0 means e to power 0, but e to power 0 is also 1. So this means that this e to the power of c is actually equal to 1. Yes? Okay, and then I put this back here into this formula, and what I get is that g of theta is indeed equal to f of theta. For all theta in R. Yes? So I'm just repeating again, this is not a proof, but that is a good motivation about the Euler's formula. So what we learned is this. If theta is a real number, then e to power I theta is equal to cosine theta plus I sine theta. This is called the Euler's formula. So Euler's formula. Yes? So this tells you that if you have a theta, a real number, I have emphasized here, e to power I theta becomes cosine theta plus I sine theta. Yes? And for this one to be right, because you see that to motivate this, I was using the derivative of cosine and sine. For example, I wrote that the derivative of cosine is minus sine, and I wrote the derivative of sine is cosine. But do you remember that these formulas for the derivatives of sine and cosine are only valid if I am working in radians, not degrees. So this is important, that for this formula to work, theta should be expressed in radians. So let me also emphasize that. Okay, so that is the formula that we had now. Yeah, is that understandable? Yes? So we found a formula for e to the power of I theta if theta is a real number expressed in radians. So this means that this will not make sense. You will not see this. Yes? This is not possible, but be careful. This is not wrong to write this. This is a valid expression. This is not wrong, even though theta is expressed in degrees. But the point is that if you express it in degrees, you shouldn't expect that these two be the same. Yes? If you want these two to be the same, you have to express theta in radians. In that case, they are the same. Otherwise, they are actually they differ by a constant, which you can calculate, of course, that constant. So be careful. This is completely meaningful, but this is not meaningful. Yes? That should be a pure number when you have an exponential number. And if you have this one, which even though it is meaningful, you cannot say this is equal to that one. For this equality to hold, theta should be expressed in radians. Okay? But that's by the way, we can take this as somehow definition of e to the power of I theta. You can consider this a motivation, but this motivation defines e to power I theta for you. Why? Because you don't have any problems with calculating cosine theta. You don't have any problems with calculating sine of theta. And if you know these two numbers, you can put them here, you find your complex number. So this, you can consider it as a definition of this exponential function. And this is the motivation behind the definition, why this definition should work. Okay. Let me... So for example, if I ask you what is e to the power of I pi over 3, this is completely reasonable expression to write in complex numbers. And I can, if I want to write it in a standard form, it's a complex number, by the way. So you see that e to power I theta is a complex number. If I ask you what is the real part of e to the power of I theta, you answer it is this. What is the real part is cosine. What is the imaginary part is sine. Yes? So if I ask you what can I write, can you write this in a standard form? The answer is simple, yes. So what you can do, you can use the Euler's formula and then write cosine pi over 3 plus I sine pi over 3. Yes? By the way, it's interesting to see this is the polar form. So if I ask you what is the polar form of this complex number, you don't need to do anything. You just, when you write the Euler's formula, you get the polar form. But if you want to write the standard form or the Cartesian form, you put the number here, cosine of 60 degrees pi over 3 is 1/2. And this one is the square root of 3 over 2. So when you see e to the power of I times pi over 3, it's that complex number. Yes? Okay, now let me, for example, ask you some questions. So if I ask you what is the real part of e to power I theta, you answer cosine theta. If I ask you what is the imaginary part of e to power I theta, you answer sine theta. Okay, let me ask you another question. What is the absolute value of e to the power of I theta? Absolute of this complex number. What is the absolute value of this complex number? Because it shouldn't be hard, yes? E to the power of I theta is this complex number. The real part is this and the imaginary part is this. You want to find the absolute value. So what I'm supposed to do, I have to take the square root. I take the real part, square it. So this is the imaginary part. I take the imaginary part, square it, and plus the real part, square it. Do you agree? That was the definition of absolute value. But that's a famous trigonometric equation, yes? Identity. Sine squared plus cosine squared is 1, so it becomes a square root of 1, which is 1. So that's also good to add to your list. E to power I theta is equal to what? Is equal to 1. Absolute value of this number is always 1, regardless of the value that you choose for theta. Okay, let me ask you another thing. What do you think will happen here if I have e to power I theta and then I want to take the conjugate of this number? What do you think will happen? So the only thing that you have to do is, instead of e to power I theta, you write cosine theta plus I sine theta. And then what do? You put this bar on it. But you learn what to do with this bar. If I want to take the conjugate of a complex number, I keep the real part exactly the same. I change the sign of the imaginary part. So this becomes cosine theta minus I sine theta. This is not wrong. Of course, that's the correct expression, but we can write it in a better way so that you can see the connection immediately. Instead of cosine theta, I hope that you agree that I can write cosine minus theta, because there is no difference between cosine of minus theta and theta. But then in here, instead of writing it negative, I write it positive, but I move the negative sign to this argument, yes? Why is that? Because we learned in chapter 1 that sine of n minus an angle is minus the sine of that angle. But now if you look and compare this one with the Euler formula here, that's exactly the same combination except that theta has changed to minus theta. So this means that if I use the Euler formula, it becomes e to the power of I minus theta. Yes, is that understandable? But instead of writing I times minus theta, I can write e to the power of minus I theta. So we can also add this into our list. So if I have e to the power of I theta, and I want to take the complex conjugate of that, what I need to do, I need to take the complex conjugate of the exponent only. Because if I ask you what is the complex conjugate of this, you change theta to minus theta, you will get that. So this becomes just minus I theta. Yes? So that's also a nice property. The complex conjugate will affect only the exponent. Yes? Okay, but now if I ask you what happens for e to power I theta 1 multiplied by e to the power of I theta 2. What do you expect? If the arithmetic is the same as before, which is the first promise that I gave you, I don't want to change the arithmetic. So this means that what you expect is to be e to the power of I theta 1 plus I theta 2. Yes, this is what you expect. But let us double check if that's correct or not. Of course, nobody writes it like that. We can write it as I theta 1 plus theta 2. Yes. But this will work. Why? Because if I start from the left-hand side, if I ask you what is e to the power I theta 1, the only thing that you can tell me is to use the Euler's formula for theta 1. Yes. And then multiplied by this one. Now my question is that, do you remember this is the polar form of a complex number multiplied by the polar form of another complex number? Do you remember what was the rule if you want to multiply the complex numbers in the polar form? Of course, one way is to start multiplying things one by one, but it becomes a little bit lengthy. I told you the very nice relation, what will happen. Do you remember? Yes?
I have my notes.
Yes?
So you just add the theta 1
to theta 2. Yes,
yeah,
exactly.
theta 2.
So the angles are added. Of course, this we have already proven, yes? But if you want to do it from scratch, you have to start multiplying things one by one. But if you do it at the end, you will get this relation, exactly the same combination but for the sum of the angles. Yes, this we already had. Okay, and then if I ask you, what do you see here? You see that you have the right-hand side of Euler's formula, but the angle theta has been replaced with theta 1 plus theta 2. So if you want to use the Euler's formula, it becomes I theta 1 plus theta 2. So I mean that what you expect is satisfied here. So that's not any contradiction or inconsistencies, yes? So from now on, do whatever you want to do with powers exactly as. For example, if I ask you, can you guess what will happen if I have this one divided by this one? What is your expectation from arithmetic? You don't need to memorize anything. So what is your expectation? Your expectation is to be able to write e and then subtract the exponents, yes? So that is your expectation. But that expectation is also true, because then you have to divide two complex numbers, and if you just again refer to your notes, you will see that the same formula is valid, but you have to subtract the angle. So that's also correct. So what you expect, that's very good, because you don't need to memorize something new. Whatever you feel natural, it's also true. Yes? Okay. So now, what do I mean? I started the title exponential form of the complex numbers, but I think now you understand what's going on. So if I give you a complex number x plus yi, yes, in Cartesian form, what you can do, you can write it in the polar form. Do you remember? The polar form is writing the same complex number as in this form. Start with r and multiply it by cosine theta plus I sine theta. So if this is called the polar form, yes? But if in this case you have to remember, if I ask you what r is absolute value of z. And then if I ask you what theta is the argument of z, which is the angle that the vector corresponding to z makes with the positive real part. Okay, and now today we also learned that this can be written more compactly using Euler's formula. Yes, so then I can write this as z equals to r e to power I theta if I use the Euler's formula for this part. And this one is called exponential form. So we have three forms for a complex number. The standard one or the Cartesian one is of this form, and then this one is the polar form. And because the Euler's formula is valid for this part, I can replace it with the exponential form, and then you get this package as the exponential form of my complex number. So if you have your complex number in the exponential form, the real number that appears here is the absolute value of your number. And theta that appears here is this theta, but that theta is the argument. So if I ask you to write a number in exponential form, that is very easy. You just write it in the polar form, as we learned before, and then use the Euler's formula to change it to the exponential form. Okay, so for example, if I give you let me write here before cleaning. So if I give you z1 to be r1 e to the power of theta 1, and if I give you z2, r2 e to the power of I theta 2, and for example, if I ask you to multiply them, you multiply normally. You multiply r1 by r2, you multiply this exponent by that exponential by that exponential, but you realize it becomes e to the power of theta 1 plus theta 2. Yes? So you can just discover these formulas yourself. Any questions? But still something is left to answer, and we have to define now. That's the definition. So you see, today when I wanted to talk about this exponential form, my question was, if I give you a complex number, whatever it is, what is the meaning of what is a meaning that I can give to e to power z consistently, in consistency with other parts of mathematics itself? But we haven't addressed this question fully yet. I only considered a very special case in which the real part is 0. If I have a complex number in this form, then we address this question, what is the meaning of e to power of I theta? But now everything is ready, we can define e to power z for any complex number z, okay? So now let us go back to the same question. So let me give you a complex number. I do not assume that x is 0 this time. Yes? And now I want to define e to power z. I want to define this expression for you. But let me ask you yourself, how do you define this? For example, I want to ask you, can you imagine a meaning for this expression? So for example, this is a complex number, 1 plus pi over 3 times I. If the 1 was not there, you know how to answer this question using Euler's formula, yes? But now what happens if I have an extra number, real number, the real part is not 0 this time? What do you expect? Yes?
That you can follow the e, so it's e to the pi over 3I times
E. Yes, that is the natural way to think. I'm just telling you, this is not a proof. This is the way that it seems natural to define it in that way. Yes, because if everything should remain the same, if everything is supposed to remain the same as the real parts, we expect that this should be e to power 1 times e to power I pi over 3. Yes, but then I do not have any problems with this part at all because that is in the realm of real numbers. E is just the normal Euler number. I'm raising it to power 1, so I don't have any problems with that. And I don't have any problems with this one either because this is now the Euler's formula. So this means that this is a good way of defining e to power of z. But that's the motivation. So that's correct. So if I want to define e to power z, I would say e to the power of x plus yi, and as Jonathan mentioned, this can be viewed as this. Yes? But now look, do I have any problems with this part? No, because e to power x is a real number. I do not have any problems with real exponential functions. The only problem might be this one, but this is also resolved using the Euler's formula. So this means that this becomes e to power x, and then instead of this one, instead of theta, I have y. That's no problem. So this becomes cosine y plus I sine y. So I would say that definition let z be equal to x plus y be a complex number. Then e to power z is defined as follows. So you might say that why we define it in this form. I would say because this definition is natural. Natural in the sense that it keeps the consistencies with other parts of mathematics. What we expect, because my expectation from my previous knowledge in real numbers is that this should be valid. That's the most natural way to define it. So I would say that e to power z is defined to be e to power x. X is the real part of z, multiplied by cosine y. Y is the imaginary part of z, yes? So x, the real part of z, and then y is the imaginary part of z. Yes? So that's the definition of a complex function at the end. Of a complex exponential function at the end. Yes? For example, if I ask you to, what is the meaning of this question mark? So e to the power of 1 plus pi over 3i, then we know what happens. According to this definition, I need to write e and raise it to the real part of my complex number, but the real part of my complex number is that, and then multiply it by cosine of this number plus I sine of that number. And then in that case, you should simplify. So this becomes e to the power of 1, which is e, but this number is 1/2, and that number is the square root of 3 over 2i, and I prefer now to multiply, so it becomes e over 2 plus e square root of 3 over 2i. So that complex number written in this exponential form, if you want to write it in a standard form, it is this complex number. Yes? For example, let me now ask you some questions here. So what is the absolute, so let me write this, let z be equal to x plus iy. I want to answer these questions. What can you say about e to power z absolute value? This is one question. And what can you write about ez totally bar? I want to find the conjugate of this complex number. So how can I answer these questions? Okay, so for the first question, e to power z is expressed here. So if I want to find the absolute value of that, what I can do is this. So the absolute value of e to power z means the absolute value of e to power x times cosine y plus I sine y. But do you remember we had this before? Of course you can multiply. So, I mean, it's easier to say the absolute value of the first one multiplied by the absolute value of the second one because we had this formula before. Yes? But let me start from scratch. Okay, so what I do, I multiply this in. It becomes e to power x cosine y plus I e to power x sine y. If I ask you what is this is the standard form of this complex number. And now I want to take its absolute value. So what I have to do, I have to take the square root. I have to raise the real part to power 2. I have to raise the imaginary part to power 2. Yes? And I have to add them. But this one to power 2 means this one to power 2 times this one to power 2. So this becomes equal to e to power 2x cosine squared 2y. Cosine squared y, sorry. And then the second one, for the same reason, it becomes e to power 2x sine squared y. But you see e to power 2x is common, so I can pull it out. So it becomes e to power 2x, and then I will have cosine squared y plus sine squared y. But sine squared plus cosine squared is just 1, so this becomes the square root of e to power 2x. So, but this can be written as e to power x to power 2, and it becomes absolute value of e to power x. But I don't need the absolute value in this case. Why? Because x is a real number. X is the real part. So it's a real number. And e to power any not real number is positive. So I don't need to have this absolute value sign. This becomes simply e to power x. So that is interesting. So if I ask you what is the absolute value of this exponential function, it becomes e to the power of real part. So in principle, if you want to write it as a formula, you can say that e to power z absolute value is equal e to the power of real part of z. So the imaginary part doesn't play any role in this absolute value number. Whatever the imaginary part is, the absolute value is only caring about the real part. Yes? Okay, so let me also get a formula for this one. Okay, so if I want to do the other one, z is equal to x plus iy. My question is that what happens if I have e to power z and I want to find its conjugate? Okay, so let us just do that. So if I ask you what is the question mark is e to power z totally conjugated. But then it means that you have to write, because whenever you want to calculate the conjugate, you have to write the complex number in its standard form. So this means that this is e to power x cosine y plus I sine y totally conjugated. But let me don't start from scratch. Of course you can start from scratch, but you really don't need to do that. So this becomes e to power x. Do you remember I can use the Euler's formula here? So this becomes e to the power of iy, and then totally conjugated. But this we had before, so let me use this one this time. Of course you can start from scratch again, but you don't have to. So if I have z times w, and then I want to conjugate it, I can conjugate the first one, conjugate the second one, and then multiply the conjugates. So I can do the same thing here. So this becomes e to the power of x conjugate multiplied by e to power y conjugate. But what is e to the power of x conjugate? What is the answer to that one? What type of number is e to power x? Remember, x is the real part. So e to power x is nothing new. It's what you just learned in Math 3C for exponential functions, yes? So this is a real number. E to power x is also a real number. And you want to conjugate a real number. Do you remember? If you want to conjugate it, what's the answer to 5 conjugate? It's 5 itself. Why? Because 5 can be written as 5 plus 0i. And this means that 5 minus 0i. But 5 minus 0i is the same as 5. So if the number is real, the conjugate is itself. So this becomes e to power x itself. But if you remember, when I talked about the Euler formula, I calculated this one for you. Instead of having y, I wrote theta. And then we got the result. The result was e to power of minus I theta. So this becomes e to power of minus iy. So if you refer to your notes, you will see that I calculated this before. And I got this result, yes? So I just use that. And now what happens here? You can combine them back again. But now if I ask you what is this, the answer is simple. Z is this number, so what is Z bar? Z bar is x minus iy, which is exactly the expression that appears here. So this means that this is nothing except e to power Z bar. So it's a nice relation. So, I mean, it's better probably to write this in a pair of brackets. So if you have this e to power z and you want to totally conjugate the expression, the only thing that you need to do is to conjugate the exponent, whatever it does. For example, if I tell you what is e to power I plus 2i, 1 plus 2i, totally conjugated, you can just write e to power 1 minus 2i. Just conjugate the exponent. Okay, before finishing this part, there is let me calculate this one, e to power I theta, using the Euler's formula. What's the answer? This becomes cosine pi plus I sine pi, yes? But then cosine pi is minus 1, sine pi is 0. So this becomes minus 1. So this means e to power I pi is equal to minus 1. And if you move this to the left, e to power I pi plus 1 equals 0. By many people, this is the most beautiful equation in all mathematics. Yeah, because it is simple and elegant, and you have all fundamental constants, many of the important fundamental constants of mathematics there, yes? 0, 1, I, pi, and e. All gathered in one simple equation, yes? So many people consider this as the most beautiful equation in mathematics. Because you know that e and pi are really fundamental constants in mathematics. I is also very fundamental. 1 and 0 also, you know that. So all of them are gathered in a very simple, nice form. Okay, so now let me consider the last part of the lesson today. And that is, we want to talk about what happens if I want to have sign of a complex number. Okay, for example, what is the meaning of sine of 1 plus 2i? We want to answer this question. But before doing that, again, we want to do the same strategy. Instead of tackling this hard problem, the harder problem, we want to answer what happens if this is 0. Yes. Because if that is 0, we can immediately find it. How? Can you tell me? So you see, my question is that I want to answer this question. What is sine of I theta? And I can also answer the same question for cosine I theta. Here I assume that theta is real. So you see, I want to define trigonometric functions, but in the realm of complex numbers. Again, the same strategy. Instead of tackling the hard problem from the beginning, let us calculate these two. But this is not hard. Why? Because if I ask you what is e to power I theta, you will tell me this is cosine theta plus I sine theta, yes? Let me see. This is not a good starting point. I might be the good starting point is probably to start with the general form. Okay, let us just ask this question. So what is, so let z be equal to x plus iy. We want to understand what is sine of z. Right? What is a good definition for sine z and cosine z? Yes, we want to understand what is that. So for example, we just learned that e to power z is equal to e to power x times e to power iy. We just learned that, yes? No, it's not working in this way. Let me think. Okay, no, this is not the. This is not the logic. Okay, so the same is that. The question is correct. I have a complex number. I want to give a meaning to sine of the complex number and cosine of the complex number. Okay, I cannot prove them. I want to define them because we don't know yet what is sine of a complex number. Prove means you already know what is the meaning of sine of z. You want to show that yes, this is also happening in this context. We don't know what is the sine of a complex number, by the way. We don't know it. Yes, but we want to understand what is a good definition for sine of z. Okay, for that, let me start with this formula. For the Euler's formula for theta, and I also define it, I also write it for minus theta. But cosine of minus theta is equal to cosine of theta, but sine of minus theta is minus I sine theta. Yes? Let me add these two. This one plus this one is equal to this one, and this one are actually cancelled, but this becomes 2 cosine theta. So you see here, by the way, in this formula theta is real. So this means that for real numbers, theta, I was able to prove cosine theta is e to power I theta plus e to power minus I theta divided by 2. If I ask you what I have done, you can say you have proven that cosine theta is equal to this expression if theta is real. So it means that if this is your normal cosine function that you learned in chapter 1, today we learned that there is a connection between that cosine and this exponential function in the realm of complex numbers. This is a proof. It's not a definition. Yes? I can do the same thing for sine of theta. What I can do, instead of adding them this time, I subtract them this time. Yes? This becomes minus that one. But this one, let us do it in our head. When I multiply this by minus sign to subtract them, this becomes negative, this is positive, that's gone. This becomes positive I sine theta, which will be added to that one. It gives me 2I sine theta. And then you divide by 2I, you proved another formula. So that sine of theta is e to power I theta minus e to power I minus I theta, but divided not by 2, divided by 2I. So you see, I just want you to understand, of course this is the only one in your book. The book hasn't talked about these things. But I can talk about this, it's not hard. Then I would, using these formulas, it motivates me to define sine of z and cosine of z for complex numbers. This I would call optional. This is not in the book, okay? So if I want to, I put semicolon, means define to be equal. There is no proof. I am defining what is the meaning of sine of a complex number and cosine of a complex number. So, but these formulas, which I was able to prove, motivates the definition. So I would say that it was valid, this formula is valid when theta is real. So let us consider that this formula should also be valid by definition if theta is a complex number. So this means this is the definition of a complex number, of a complex sine function. Sorry, this one is the definition. So I have to keep iz minus e to power of minus iz divided by 2I. And the same thing using this one for cosine. Let me make sure. So you see I theta iz minus I theta minus iz. Oh, sorry. This is the difference and this is 2I. So that's for sine. For cosine, I have to copy and paste this formula somehow. This becomes minus iz divided by 2. So this is optional. It's not in the book, okay? But I want you to understand the logic. I was not able to prove this for you rigorously, but I motivated you why the Euler formula is correct. Now, so it means that in principle, we can prove this formula. Using this formula for theta and minus theta, I was able to prove these two equalities. That's a proof. But now, this is not a proof. That is because if I ask you what is the proof, prove it, it means that you already know what is sine of a complex number. You already know this and you prove that they are equal. Yes, but you don't know what is sine of a complex number. This is not a proof. That's the definition of a complex number, sine and cosine function. So this is theta real. Z, any complex number. Okay. So I want to draw your attention to some. So there are some properties that you might not expect. You know, for example, for exponential functions, let me just first talk about the exponential functions. For example, let me calculate e to the power of 1 plus pi I for you. Yes? If you calculate this, this becomes e to power 1 times e to power pi I. But do you remember, e to power pi I, I told you that's the most beautiful formula in mathematics, it's minus 1. I don't want to calculate it once more. So this becomes e times minus 1. But then the answer becomes minus e. Okay? But this should be a little bit strange for you. Why? Because e is a positive number, minus e is a negative number. So this number turns out to be a negative number. So don't think that this is wrong, because your intuition is that exponential functions are positive. So the output of an exponential function cannot be negative when you are working with real numbers, yes? E to any power, even if the power is negative, it's a positive number at the end. Okay, so this is possible. When you are working with complex exponential functions, you might get a negative value if you have done the calculations right. So that's not a surprise. Because if you remember, I told you that we cannot compare the complex numbers, which one is bigger, which one is smaller. So in principle, minus e is a negative value, but if I say e to power 1 plus pi I as a complex number is less than 0 as a complex number, first I have to define the order. Okay, so which we don't know. Okay, so here, these strange things might happen. Okay, so I will not probably continue this one. Might be we will solve some problems using these definitions. These are definitions. Those are proofs. So the one up there is included in the book. Let me give you an example which is good in the book. So do you remember in chapter 2 we were able to prove this. Oh, sorry, in chapter 1. Okay, so let me write this. Cosine 2 theta is equal to cosine squared theta minus sine squared theta. Yes, this is a famous double angle formula for cosine. But now we can prove this using complex numbers in a different way. How? For example, let me start from the right-hand side. The right-hand side is equal to, instead of cosine theta, I can write this formula, yes? Cosine theta, I can write this. And for sine theta, I can write this. So let me just put them here. So the right-hand side will read like this. It becomes e to power I theta plus e to power minus I theta divided by 2 totally squared. And then I have negative sign, and instead of sine theta, I would write e to power I theta. That's the second formula here, yes? So it's e to the power of I theta minus e to power of minus I theta divided by 2I squared. And let us simplify this. So this fraction to power 2 means the denominator to power 2, which is 4. And then I have to use the squaring rule for squaring this one. So this becomes the first one squared 2 times the first one times the second one plus the second one squared, yes? And then I have negative sign here. And then I have this one to power 2. But the denominator to power 2 is 4I squared. But I squared is negative 1. So the denominator becomes negative 4. But then I will do the same trick here. So the first one squared, 2 times the first one times the second one, and the second one squared, yes? And let me simplify this. First of all, you see this is minus, and that's also minus. So I can just get rid of them, it becomes positive. And this becomes 4 and 4. So the common denominator is actually 4. But remember, I have to add them, not subtract them, because I have already considered this negative sign as well. This one, let me write it. This one is 1, yes? E to the power of I theta, e to the power of minus I theta becomes e to the power 0, which is 1. And then I will have this. And then, remember, this is positive sign. So this becomes e to the power of 2I theta. This is minus 2. And the other one is e to the power minus 2I theta. Yes? And now what happens? This 2 and that 2 are cancelled. E to the power 2I theta, another one here. So this becomes 2 times e to the power of 2I theta. But here I have, again, the same thing. E to the power of minus 2I theta, another one here. This becomes 2 e to the power of minus 2I theta divided by 4. Yes? But now what I can do, I can factor a 2 out in the numerator. Yes? So what I can do, I can factor a 2 out. It becomes e to the power 2I theta plus e to the power minus 2I theta divided by 4. But these 2 and that 4 are simplified. And if you don't mind, instead of writing 2i theta, let me write e to power I and then write 2 theta close together, okay? And I will do the same thing here. E to power minus I, 2 theta. And then instead of dividing by 4, I divide just by 2 because it has already been simplified. Now compare this formula here with the right-hand side of the first formula. Everything is identical except that theta in both cases has been replaced by 2 theta. Yes? So if this one is cosine of theta, this one is cosine of 2 theta, yes? So instead of that expression, I can simply write cosine of 2 theta. And that is equal to the left-hand side. So you see, this is an identity not in complex numbers at all. If you remember, we also proved this in chapter 1 without knowing anything about Euler's formula and things like that. But that is another method to prove this one. And by the way, I would consider this method easier than the one that we chose in chapter 1, because in chapter 1 we have to be creative to be able to prove the addition formula for cosine using geometry and cosine rules and things like that. And then using that we were able to prove this formula. But this one might be a little bit lengthy. By the way, it's not that lengthy. You want to calculate some of them in your head. But this is algebra and simple, without any creativity. Yes, I just put the formulas there and I simplified and I got my result. So you see that if you know complex numbers, you can also prove a lot of things about real numbers, but using the complex numbers I would consider this easier, because if you want to do it algebraically, you just plug the formulas in and calculate. You don't need to be really creative at all, just simplify. So I would say that this is easier for doing it. Okay, any questions? Okay, so I will update the Google Classroom for which part you need to cover if you want to study on your own. Thank you.